Thank you, Anton. Thank you for having me. Please interrupt me and ask questions whenever you have. This will be a little bit a change of topic. It's not going to be a mathematical talk, but it's going to be a physics talk. Nevertheless, I think things which were discussed just in the previous talk by Arthur will be relevant for several of the slides, which you will see. Okay, I will first start with an introduction and then talk a bit about what very large surveys of galaxies, so surveys which just count galaxies in position in the universe, what they actually measure, what we can measure with them. We'll talk about kind of the simplest statistics which we form with them and show how we can measure the lensing potential, which is just a weighted gravitational potential along the line of sight to these galaxies, and how we can use this to test the theory of gravity with, for example, the EG statistics, or by measuring the growth rate of perturbations. As you all know, Einstein's theory of gravity has been extremely successful with comparing it to experiment. I mean, the first thing which made Einstein famous was the light deflection around the sun. Light deflection is nowadays used in astrophysics and cosmology to measure masses. It has become a tool, an everyday tool. The perihelion advance of Mercury was the first thing which Einstein really calculated with this theory. And in the meantime, we don't only have these 40 arc seconds per century perihelion advance of Mercury, but we have systems which have perihelion advance of degrees per year and stuff like that. This also has become a very standard technique. Then Shapiro time delay and many other classical effects of general relativity have been studied and measured successfully. It's the time delay due to the light going through a gravitational field. That the distance, if you set the speed of light to unity, the distance and the time are not the same anymore. And lately, or 5 years ago now, also gravitational waves have been detected. So general relativity is as successful as it can be. However, first of all, these observations are typically on scales of the solar system or smaller. The objects which are used to test GR are usually black holes or heavy stars, but not much larger scales. Furthermore, they are all essentially tests of the vacuum equations. Black hole solutions are vacuum solutions, and gravitational waves are vacuum solutions. So we have mainly tested GR on vacuum solutions. There is one, so the question is, can we also test it with matter present, where we have on the right-hand side the energy momentum tensor of the matter around us? Cosmology would be such a situation, because cosmology on very large scales, we actually assume that on very large scales, the geometry is homogeneous and isotropic. So the 3 space is a space of constant curvature, this metric gamma, and we only have the size of it, which can depend on time only. If we make this very simple assumption for the metric of space-time, the equations boil down to a dynamical equation for this expansion factor, which will depend on the one hand on the curvature, on this curvature of this space, 3-dimensional space of constant curvature, and on the other hand, on the matter content of the universe, its energy density and its pressure. What one can add to Einstein's equation, as you probably all learned in a course on general relativity, is a so-called cosmological constant. And this cosmological constant on this the expansion of the scale factor also depends on this cosmological constant. I put it here because you will see for most of the rest of the talk that this cosmological constant is actually very relevant in cosmology. It's completely irrelevant if you want to describe the metric in the vicinity of the solar system, because the gravitational field due to the sun is so much larger than this cosmological constant that you can just set it to 0. But in cosmology, it's very relevant. So in cosmology, we have made many observations. So have we tested these equations? Let us think a bit more what we have really done, what measurements have we done, and whether they really test these equations. What one can introduce is the so-called luminosity distance. If we have the flux, which comes from an object, here I forgot to say, if space-time is expanding, a source which emits light at the time t, which arrives at us at present time, we call it t0, when the scale factor has expanded to a0, such light will be redshifted, and the redshift factor c+1 is given by the ratio of these two scale factors. This is something which we can measure very, very easily. We just look at some hydrogen line from the star. We know what its wavelength is in the laboratory, so we can see how much it has been redshifted by coming from this object far away into our telescope on Earth. The flux coming from some source can also be measured. And if we would have Minkowski space, we would say the flux is given by the luminosity divided by the surface which, on which we lie around the object, which is 4 pi distance squared. This distance is called the luminosity distance. And in this kind of geometry, it is easy to compute. It's given by this expression where chi here is the sinus with the curvature. If curvature is 0, you have just to take the limit, and then this chi function is just equal to r. Otherwise, it's this. If curvature is negative, this square root here becomes imaginary, but the ratio is still real. So it's always this function which can easily be calculated, and it depends, as you see, on h of z. H is a dot over a on this expansion rate, on the rate of expansion of the universe, which itself is given by the energy density of matter and the cosmological constant and the curvature. If I would know these quantities, I could calculate this function. So in other words, if I measure the flux from many, many objects of which I would know the luminosity, I could measure this function, and therefore I can measure this function. And therefore, if I measure this function for many different values of z, I can take its derivative and measure h of z. And this is actually what we have done, not me, but what observers have done. They have supernova of type 1 are objects of which we know quite well the intrinsic luminosity. I'm simplifying here a little bit. All these things have lots of details attached to it, on which some people could make an entire course, which I will not do here. And so we can measure this function. This has been done. Here, these are data points. Here, this axis is proportional to the logarithm of this luminosity distance. That's the redshift. And there are different models here shown. You see here, if this curve here becomes negative, this means that the universe is actually decelerating, which is what we usually would expect, right? If we all know gravity is universally attractive, so the expansion from the Big Bang due to the presence of matter should become slower and slower and slower if matter really breaks this expansion rate. So we would expect naively a curve somewhere in this regime. Depending on what the matter content is and what the curvature is, this is what we would expect. If a universe is only has negative curvature, but neither matter nor a cosmological constant, then you have a so-called Milne universe, and this goes here. This is the here we show the difference between a Milne universe and our true universe. So the Milne universe in this difference is of course 0. And if a universe is accelerating, only contains a cosmological constant actually gives an accelerating universe, then you would see something like the red curve. What we truly have observed is well fitted by the blue curve, where 70% of the expansion rate is due to a cosmological constant and 30% is due to the presence of matter, and there is no curvature. That's a relatively good fit, as you see this blue curve. This is, yeah, there are newer data which tell the same story, but what is important, Jean-Pierre?
Explain to the mathematicians how the time runs relative to that.
Okay, so maybe for this we can go. Here you see, this is the redshift, and this is the ratio A0 over A. The universe is expanding. If you go back in time, A was smaller. So if you go back in time, the redshift is larger. The further away, the further redshifted we see an object, the further away it is from us. But does this mean, so okay, we see this blue line, which is a good fit, and which we can model by having a cosmological constant, which makes 70% of the expansion rate, and matter, which makes 30% of the expansion rate. This omega tells you what is the fraction of the expansion rate, which is due to a given component, be it cosmological constant, matter, radiation, curvature, spatial curvature. And however, what we have done here is we have postulated the equation, right? We have postulated the equation because we measured only one side of it. We only measured the expansion rate, h of z, via this distance measurement, but we didn't measure the matter content. So we should actually now go and count galaxies to really see what the matter content of the universe is. For example, that would be one possibility, which has been tried since a long time, but is very difficult because most of the matter in the universe is dark, so we don't see it. So it's difficult to estimate what mass it has. Here is a somewhat newer compilation. But since the plot is not so well done, let's not comment too much on it. What I want to discuss in this talk is that if we go beyond this geometry, this homogeneous and isotropic geometry, and take into account that actually matter is clustered on smaller scales, that we have galaxies, we have huge voids, we have filaments of galaxies, clusters of galaxies in the universe. If we take that into account, we can actually do a bit more. The way we do that in cosmology is we use correlation functions, right? We determine what is the probability, if I know I have, let's say, a galaxy at position Q, what is the probability above the mean density to have also a galaxy at position P? That's basics of correlation function. And furthermore, what I also have to say here is our idea is the following about how it came about that the universe, the galaxies and all the structures which we observe in the universe were formed. The idea is that there was a phase of very rapid expansion of the universe, which we call inflation, which one can make if one has the energy density of the universe dominated by a scalar field. And if one has this rapid phase of expansion, then you have quantum fluctuations in this scalar field. They are coupled to the expansion, so they are coupled to an external classical rapidly evolving field. So they are amplified. So you amplify classical fluctuations in amplitude, and then they are stretched to very large scales. And you can calculate two important properties of these fluctuations. First of all, they are nearly Gaussian. They have very, very small non-Gaussianities. And secondly, they are nearly scale invariant. They have a spectrum which is very, very close to scale invariant, which means the amplitude of the fluctuations is nearly the same on all scales. So assuming this nearly scale invariance, which one can quantify more precisely, and assuming that initial fluctuations are Gaussian, if they would be perfectly Gaussian, they would be determined by the by the two-point function alone, right? All the higher moments, you get them via Wick theorem. Now they evolve afterwards during the normal expansion of the universe. Once the scalar field is more or less wiped out, has disappeared, they evolve via the equations of general relativity, which are nonlinear. And you know that if you apply some nonlinear transformation on a Gaussian field, it's no longer Gaussian. But as long as these fluctuations are small, you can linearize these equations, and the evolution is nearly linear. And so the field remains nearly Gaussian. And you can then compute and measure its two-point function or power spectrum. This has measured in the past very precisely with the so-called cosmic microwave background, CMB, which is the relic radiation in the universe. Most of the photons in the universe are actually this CMB. When the universe cooled down sufficiently so that electrons and protons combined to neutral hydrogen, it became transparent for photons. And these photons just, the only thing they did then, they did no more scattering, and they just grew their wavelength. But otherwise, they kept a very thermal spectrum, and they kept the input fluctuations which they had from inflation. And these fluctuations have been measured. Have been measured. Here you see height of projection of the sky, and here you see the power spectrum, the measured power spectrum, compared to a calculation, which is the blue line. This blue line is a calculation which inputs 5 parameters, 5 basic parameters and 1 kind of fudge parameters. These are the amplitude and spectral index of this primordial power spectrum from inflation, which is nearly Gaussian, the amount of matter in the universe, the amount of baryons in the universe, and the value of the Hubble constant or the expansion parameter today. That's the input parameter, as well as some fudge parameter, which I will not discuss here. And you see these are about 2,500 points fitted with 5 input parameters. So there is something we understand here. This is very nice measurement of the early universe, and most what we know about cosmology comes exactly from this data. There are several assumptions. For example, we assume that the process which generated these fluctuations, typically inflation, is statistically homogeneous and isotropic. And if it is isotropic, these temperature fluctuations here, which are characterized by the stochastic coefficients ALM, the expectation values of these coefficients are diagonal. Now, we would like to kind of repeat this success story by looking at galaxies. There are several complications because what we typically calculate is the fluctuations of the density field, and galaxies are kind of discrete tracers of this density field. What we assume is that galaxies form in local peaks of this density field, local peaks above a certain threshold. And if fluctuations are small, they are Gaussian, and we know everything about local peaks of a Gaussian field. So things can be calculated what the statistics of this galaxy distribution should be on sufficiently large scales at sufficiently high redshifts. What people have done so far is things like this. They have said, okay, we have these galaxies, let's Fourier transform this distribution in three-dimensional space and calculate the power spectrum. They have calculated this power spectrum. They see also these fluctuations, which we have seen also in the oscillations, which we have also seen in the CMB and which I did not explain. They actually come from the fact that if you couple photons and baryons together, then the photons, they really oscillate like acoustic waves. They make such acoustic waves, and the CMB is like a photo of these waves when the universe recombined. And so at these moments, you had some wavelengths which were in a maximum, others which were in a minimum, and they leave exactly this kind of fluctuation, oscillation imprint, these acoustic oscillations on the CMB power spectrum. You see them also here. They are much less pronounced because most of the matter is dark matter, is not baryons, and does not couple to photons, and therefore does not participate in these oscillations. However, the baryons, this is also a way to measure the baryon content of the universe, and this has been looked at so far. As long as we have relatively small galaxy catalogs, that's a good thing to do. But once we have bigger galaxy catalogs which go all through the visible universe, we have to take several additional things into account. First of all, we have to take into account that all measurements which we can never measure 3D space. We can only make measurements on our background light cone. And we typically measure in cosmology, we measure 3 angles and a redshift. But the measurement of this redshift is perturbed by our peculiar motion, but also by the gravitational potential which is present. Furthermore, not only the number of galaxies in a given patch, but also the volume itself are perturbed. And the angles we are looking into are not the angles in which these galaxies actually lay because of light deflection. So there are all these kind of light cone effects which are irrelevant as long as the galaxy catalogs are small and go out to redshift 0.1, 0.2. But once we go to large redshifts, as we want to do in the future, they will become very important. So let us look at this a little bit in more detail. If you calculate the co-moving distance out to a given redshift, again, you have this Hubble parameter as a function of redshift. And this depends on the matter content of your universe. Here I just took as an example matter, curvature, and the cosmological constant. So the results depend on your cosmological model. And then if you measure some distance, it is this function chi of r, either the angular diameter distance or the luminosity distance. For small redshifts, all of these quantities are just given by c over h naught. For this reason, since h naught, this expansion rate, is not very well known, in cosmology, one usually measures distances in units of h inverse times megaparsec, where a megaparsec is roughly 3 million light years, and h inverse is a fudge factor parameterizing our fact that we don't know this distance, this expansion rate h0. But at larger distances, this is no longer sufficient, but we have to really know this function and we have to input these parameters. For example, so this is, I think, is an important point in cosmology and in all of astrophysics. If we talk about distances, it's always including a model. We never can we measure directions in the sky, we can measure redshift, we can measure flux, but we can never measure distance. You need a model before you have the distance. So depends on what you assume about your universe. Of course, in physics, every model is an interpretation. Also, if we measure redshift, what we truly measure. But in cosmology, it's especially important because we have so few measurements. It's not like in electrodynamics, you say, okay, if I look at my ampere meter, I need a model to interpret what current this actually means. This is not so important because you have 100,000 tests of Maxwell's equation in 100,000 different situations. In cosmology, we don't have that many tests, so it's much more important that every distance we know is model dependent. And I mean, all of astronomy is a history of wrong distances because this is really the difficult thing which cannot be done. Here, for example, the correlation function as a function of angle, converted into a correlation function as a function of distance with different cosmologies. You get something different. You get it is scaled differently, and then correspondingly, if you Fourier transform this to get the power spectrum, it will depend on this as well. So now, if you do linear perturbation theory, which is all with what I'm talking about. So if you have initially Gaussian fluctuations, they remain Gaussian as long as this linear perturbation theory is applicable. And you take into account all these light cone effects I was talking about, namely that your gravitational potential changes your light cone, etc., that your redshifts depend on the velocity of the object. If you will take all these into account, you can still, for a catalog of galaxies where you have measured positions of galaxies, what you have really measured, namely angles and redshifts, you can form this fluctuation here, the number of galaxies inside some bin, angular redshift bin, minus the mean over this sphere at this redshift, and divided by this mean, so that's this fluctuation. This is something which you can truly measure. You can truly measure its correlation function, and you can also calculate it. If you calculate it within general relativity, you get this type of formula, where I will just explain a couple of the terms here, not all of them. This is the galaxy density fluctuations, which you expect to be there. The galaxy density fluctuates. This term is the so-called redshift space distortion, which comes from the Jacobian transformation from volume to redshift, to redshift and angles. That actually comes from the Jacobian transformation from distances into angles. This first factor here. Then there is another factor here, which is S, which comes from the fact that and has the opposite sign, which comes from the fact that if you have a telescope, it has some finite flux limit. It can only see objects above a given flux. If you would see all the galaxies, you could set S to 0. But since you don't see all the galaxies, your telescope has a finite sensitivity, and there might be galaxies which are fainter than that sensitivity. And now, if you have lensing, these galaxies might just get over the flux limit of your telescope, and you would see them. So how faint galaxies you see depends a little bit on whether there is lensing between you and the galaxy, or a sufficient amount of lensing between you and the galaxy or not. So this S is actually nothing else than the logarithmic derivative of the number density of galaxies as a function of luminosity, which is something which you can measure at the limit, at the luminosity limit of your telescope. So it depends on your telescope, depends on your observational situation. And then there are other terms coming from the gravitational potential. This, for example, is the Shapiro time delay term. The phi and psi are the gravitational potentials. You see, in general relativity, you have, instead of the Newtonian potential, you have a metric, which is a symmetric 4x4 matrix. So you have 10 degrees of freedom in principle. Now you can make choose arbitrary coordinates to simplify this matrix. This removes 4 of the 10 degrees of freedom. So you are left with 6. 2 of them are spin 2 under rotations, and they describe the graviton. And they describe a freely propagating degree of freedom, the graviton. 2 of them are spin 1. They are 0 if there are no sources. These are vector degrees of freedom. 2 of them are scalar degrees of freedom, and they are also 0 if there are no sources. So they are not free propagating modes. And these are these 2 scalar degrees of freedom. Here we look only at scalar perturbations. Within linear perturbation theory, they all decouple. I could write down a similar formula for the vector and for the tensor degrees of freedom, but let's spare this. So here I just show you one very physically very intuitive term, which is this redshift space distortion, which has been measured. This is from the Boss survey. You see a squashing on large scale and an elongation on small scales. This elongation is what people call fingers of God. They were discovered in the 90s already, or in the 80s. And this squashing is the linear perturbation theory term, which comes from the fact that if you observe objects behind an overdensity, they fall into this overdensity. So they actually move towards you. So their redshift, their cosmological redshift is smaller than it would be without this motion. And therefore, they seem to, if you now convert redshift into distance, they seem to you to be closer. With those objects in front of you, it goes the other way. They seem to you to be farther because they move out. On small scales, you have nonlinear effects from the fast motion around the compact or the high overdensity or the virialized motion. And so this kind of gives you a bigger spread in redshift. This is this finger of God effect. Of course, again, here we have a function on the sphere. We can expand it in spherical harmonics now at each redshift, and we can correlate the coefficients. And again, statistical homogeneity and isotropy requires that this correlation be diagonal in L and M. And we get this power spectrum, which now depends in addition on 2 redshifts on the sphere, or the correlation function if you prefer it, where these PL here are the Legendre polynomials. You can calculate this in a given model, and typical models, you see that at smaller redshift, the density term is really the most dominant term, dominates by orders of magnitude about everything else. Whereas if you go to high redshift, here this is redshift 3, and you lose a relative wide redshift bin over which you integrate things, you find that actually the lensing term becomes very important in addition to the density term. You can also look at this function as a function of redshift for a given mode L. And again, you'll find that low redshifts, it's the density and maybe redshift space distortion terms which are relevant, while at high redshifts, the lensing becomes very important. I could also talk about the sign of these terms, but let's not do this. Let's come to something real, which this is Euclid satellite, which we hope to be launched next year, if everything goes well. There is just one thing which I still want to mention. Of course, if we measure something, we always have error bars. First of all, the CLs which we have calculated, there we calculate ensemble averages, statistical ensemble averages. What we measure, we have one universe at our disposition. So how can we measure an ensemble average? We cannot. So what we do is we assume some kind of ergodic hypothesis, namely that if we measure many ALM squares, that gives us kind of a statistical mean. One can show under the assumption of a Gaussianity, we can actually generate an estimator for these CLs, which we can truly measure, and we can calculate its variance. And we find that actually the variance here is given by 2 over 2L plus 1. So if we assume that the fluctuations are Gaussian. So, and this variance is called cosmic variance. There is nothing we can do about, you can imagine. This is, of course, if we would have data all over the sky, which we usually don't have. So the true variance is usually larger than this. So you see, for example, the quadrupole, if you put here L equals 2, we cannot measure it with good precision. But if we have L equals 1,000 or 2,000, it gets better. So if we now want to compare some calculation with an experiment, we always have to add the error bars. Here, I just show you some results, how we can measure this lensing potential, for example, with the Euclid satellite. If we correlate a bin with itself, it is totally dominated by the density. But if we correlate a foreground bin with a background bin, the densities so far away are very, very weakly correlated. However, the light which comes to us through this, from this background bin has gone through the over or under density in the foreground, and therefore its lensing term will be strongly affected by the density in the foreground. And we can actually measure, we can actually measure the correlation between density and the lensing term. Here, just as an example, we show the full result compared with only the local part of the result, which is dominated by the density, and compared the local correlated with the lensing part, which is dominated by this kappa delta term. And we see if we correlate the first bin in redshift space with itself, it's only the local terms which contribute here. However, if we correlate bin 1 with bin 4 or bin 1 with bin 10, then it's this term which is relevant. So we have now done the following thing. We have said, okay, the lensing term in general relativity, we know how to calculate it. Let us assume it would be proportional to the one in general relativity with some proportionality factor unknown, beta. How well can we determine this beta? And we have seen that if we, here I showed that we used many more parameters. We didn't do a real parameter estimation with Monte Carlo, but we just made a kind of Fisher matrix analysis, which is simplified analysis for the errors. We estimated some of the neutrino masses, the Hubble parameter, the amplitude of fluctuations, and several other parameters, which I'm not showing, but mainly this beta. You see that most parameters, they only care whether I use 5 bins or 10 bins. However, these beta parameters, there it's really very important whether I use the cross correlations also, or only the autocorrelations. So I get much better constraints on these beta if I use cross correlations. And that's exactly this effect which I told you. What we have also shown is what happens if one neglects lensing. And there we have done something which is kind of similar to these neural networks, but it was just poor woman's neural network, Monte Carlo Markov chain analysis, where we determined the best fit parameters and the errors around if one would make an analysis neglecting the lensing term. And actually, this is what people have done until today, and they still plan to do it with Euclid. But we are slowly convincing them not to do it because it's going to be wrong. For example, let me just show you one example, namely the neutrino mass. Input neutrino mass was here 0.06 electron volt, which is the minimal value for the sum of the neutrino masses if you assume the oscillation experiments. If you don't take into account this lensing term, you find a very nice measurement of the neutrino mass of about 0.3 electron volt, which is wrong. And we can also physically understand why you get that, because this lensing term does something which is similar to what neutrinos do, namely a little bit wash out small scale fluctuations. If you take into account lensing term, you don't get super good limits on your neutrino mass, but you know at least it's compatible with the input value. So what of course we all know is if you analyze your data with the wrong theory, you get wrong parameters on your wrong theory. It's not very surprising. Then I wanted to say a few words about these EG statistics. Let me see how I am with the time. Yeah. People have studied in 2007 already how one could isolate the sum of the gravitational potentials. And you see, it's actually if we have general relativity, we find that the sum of these gravitational potentials, this is a potential for the Weil tensor, and photons should only be sensitive to this sum of the gravitational potentials. While as ordinary matter is nearly only sensitive to this second of the gravitational potentials. And if matter is kind of normal and an ideal gas, you can show that both of them are equal and are equal to the Newtonian potential. So the scalar part of GR is very similar to Newtonian gravity. So what would be interesting would be to measure this quantity here.
What are two potentials?
What they are. In general relativity, in principle, you have two different potentials. One determines the time-time part of the metric, and the other the space-space part of the metric. And they needn't be the same. In Schwarzschild, they are the same, but they needn't. Depending on your matter content, they are not the same. Okay, so these are these two potentials. If we have only massive particles, they are both the same. If we have only an ideal gas, they are both the same. But if we have some anisotropic stresses or so, they can be different. Sorry?
It's just an historical accident that people call it potentials. I mean, they're just ways of describing the geometry.
They are ways of describing the geometry, yes.
One of them is the same, and sometimes it's the main potential, and that's why the other one also gets the main potential. It's not like it's another potential term.
Yeah, it's a generalized potential, and yeah, I mean the full potential of GR, you can call the metric the potential, and the connections the force, and then the Riemann tensor the tidal forces. So in that sense, it is but whatever. So this would be velocity, which you can in principle also measure, but you can show that this quantity here, you can measure it if you measure the lensing density correlation divided by the density correlations. But as I was arguing before, if you count galaxies, you not just measure the density fluctuations, but you measure all these other terms in addition. And we showed how to correct this formula that you still can measure it. Let's not dwell on this. But what is important is if you have a Euclid-like survey, and if you want to measure this EG at as a function of L, it should be independent of L, should be constant for a given redshift. And if you don't make the corrections which we introduce, you can make huge errors, especially at higher redshift. So you have to include these corrections to do that. Another thing which you can measure is the growth rate of perturbation. That also depends sensitively on your theory of gravity, and you can calculate what it should be in general relativity. What is interesting is if you compare density and velocity, then the ratio between the two gives you the growth rate of perturbations, which is called F. And so you need to have a good measure of redshift space distortion. So you want to have the redshifts very precisely. You want to have a spectroscopic survey, not only photometric redshifts, which are very less precise. And people always thought, okay, in this case, this lensing convergence is irrelevant. One doesn't have to include it. And it is true if you only want to measure the standard parameters, you find that the errors in the standard parameters from cosmic variance or from shot noise and so are larger than the contribution from this lensing potential. However, if you want to get at the growth rate, you can also make errors if you don't include this lensing. This is the true growth rate, and that's the one which you would have neglecting lensing, and these are the errors here, including shot noise and cosmic variance. And you see that this growth rate at higher redshift, you get it wrong, and you think, wow, we have measured deviations from general relativity, but actually you just haven't included a term which is important in this computation. Okay, let me conclude. One thing which I want to say, main thing which I want to say here is, in the past, people have mainly measured quantities in real space in cosmology. Correlation function or power spectrum, or then the bispectrum or higher cumulants of the spectrum, which are interesting because non-Gaussianity developed when nonlinearities come in and so. But they all require a fiducial input cosmology. So you cannot use them to test your cosmology because you need it to get at them. And furthermore, in these three-dimensional spatial quantities, it's not clear how to compute lensing, because we know how to compute it on your background light cone. But your background light cone gives you a spatial surface and not a three-dimensional space. And when you go off your light cone, there is no lensing, right? Photons move along light like geodesics. This cannot be helped. So if you want to do true 3D catalogs, your coordinates have to be an angle and two redshifts, and not three spatial coordinates. And you have to compute this angular spectrum or bispectrum. But data will be good enough to do this, and I think this will eventually be done. These quantities, of course, they depend on more variables, so they are more noisy, but they also contain more information. In principle, you can measure the matter distribution, the velocities, and the geometry using these quantities, which would really allow you to test Einstein's equation. Yeah, that's actually all I wanted to say. Thank you for your attention.
I have a question which is possibly embarrassing because it seems like I didn't understand the main point of your question. So at what point did you not have to rely on the background forms of the metric? I mean,
I assumed that the background form is in all the model calculations or which I presented. I assumed that the background form is Friedman with fluctuations. But in the measurement, when once you measure, for example, these CLs of CC prime, you don't have to assume them. You just measure. And then you want to compare with the model. So then you do something which goes along what Arthur presented us, right? You do calculation, you compare it with your model, you do steepest descent to minimize your errors, your loss function. That's exactly what we did, for example, by simulating some measurements when I presented the thing where you get the neutrino mass, right?
But just hypothetically, if it really were true that the universe is not described by a quadratic group, how would that factor into your analysis?
That would, for example, if we would measure these CLs of C and C prime, they would just not correspond to the model. But it would be a bad fit, and there would be, you see, you are right to some extent. I, of course, assumed statistical isotropy to get at the CLs, right? So what one then might also want to do, but this is not so easy, is to correlate ALMs with different Ls and see whether they are truly zero. But that's not so easy. I mean, we could talk about it. The problem is that there is a trade-off between assuming Gaussianity or assuming isotropy. You know, if they will not be zero, and what does it mean? Does it mean that my statistics is not what I assume, or that there are really correlations? So it's not so difficult, not so simple to distinguish between them. Yeah, I made the assumption of statistical isotropy. Yeah.
Any more questions or comments? Maybe I got confused about one thing. So those CL, those correlations. So there are already measurements, or this is Euclid who going to measure them for the first time?
There are no CLs from galaxy surveys measured until today. There are CLs from the CMB, and there are CLs from pure lensing measurements where people looked at the shear of which changes the ellipticity of galaxies. I didn't talk about that at all here.
So there are some measurements, and those measurements, do they roughly correspond to the expectations?
Yes,
or?
They roughly correspond. There are things which don't agree, which we don't understand, but this could be systematic errors still in the measurements, and there are things which agree well. They roughly correspond, let's put it like this, yes.
No more questions. Thanks again.